Hi, good day!
In this video, we will learn primality tests using orders of integers and primitive roots. But before we proceed to our main discussion, let us have first a short introduction of why we chose this topic. According to Gallier J. and Quaintance J. 2019, February 27, the problem of determining whether a given integer is prime is one of the better known and most easily understood problems of pure mathematics. This problem has caught the interest of mathematicians again and again for centuries. However, it was not until the 20th century that questions about primality testing and factoring were recognized as problems of practical importance and the central part of applied mathematics. This will be the content of our discussion. On the first part, we have the overview. Here, we will recall the meaning of prime numbers and introduce primality test. On the second part, the orders of integers and primitive roots. In this section, we will understand and learn orders of integers and primitive roots as this is the prerequisite on our topic to discuss. Third part is primality test. This is the main topic to discuss. We will learn here the primality test using orders of integers and primitive roots. On the fourth part, it is the conclusion. This is the summary of the discussion and the major takeaways in primality testing. Are you ready to learn something new and significant for today? If yes, of course for me it is yes. Let's proceed to our first part, the overview. The first part of this video lesson will basically answer two main questions. That is, what is prime number and why we need to do primality test. Let us continue this video lesson by learning what is prime number.
First though, do you know what a prime number is? Every prime number has exactly two factors, and they are 1 and the number itself. Or to put this another way, each prime number is only ever divisible by itself and 1. This means that 1 can't be a prime number.
If 1 is not a prime number, so what are the examples of prime numbers? The examples of prime numbers are 2, 3, 5, 7, and 11. These are the first few prime numbers. Did you get it? What is primality test? By going back to the definition of prime numbers, we verified that 13 is prime and 26 is not prime. Did we do primality test here? What do we mean by primality testing? Primality testing is the problem of deciding whether a given number n is prime. Primality test. Efficient primality tests are needed for generating keys used in many modern cryptographic systems. Worthington R. 2018. Primality tests oppose the usual decomposing of number into its constituent prime factors, which is known as prime factorization. The objective of primality testing is to take as input a positive integer and return as output a verdict whether the number is prime or composite. We are now on our second part of this video lesson. Here, we will understand and recall orders of integers and primitive roots. The order of an integer. Definition. Let a and n be relatively prime integers, with a is not equal to 0 and n positive. Then the least positive integer x such that ax is congruent to 1 modulo n is called the order of a modulo n and is denoted by order Na. This notation order Na was introduced by Gauss in his Disquisitiones Arithmeticae in 1801. Unlike much other notation used by Gauss, this notation remains in common use. Take a look with our example 9.1. To find the order of 2 modulo 7, we compute the least positive residues modulo 7 of powers of 2. We find that 2 raised to 1 is congruent to 2 modulo 7. 2 raised to 2 is congruent to 4 modulo 7 because 2 times 2 is equals to 4. So this will be gonna be 4. modulo 7. Then 2 raised to 3 is congruent to 8 because 2 times 2 times 2 is 8, which is equal to or congruent to 1 modulo 7. Therefore, order 2 modulo 7 is equal to 3. By corollary 9.1.1, if a and n are relatively prime integers with n is greater than 0, then order a modulo n divides phi of n. If you forget phi of n or how to get phi of n, it is simply the number of positive integers less than n such that the GCD of n and x is equal to 1. For our example 9.2, to find the order of 7 modulo 9, we first note that the phi of 9 is equal to 6. So how and why? Because from the definition of phi of n, the phi of 9 consists of 1, 2, 4, 5, 7, and 8. That's why it becomes 6. Since the only positive divisors of 6 are 1, 2, 3, and 6, by corollary 9.1.1, these are the only possible values of order 7 modulo 9. Therefore, 7 raised to 1 is congruent to 7 modulo 9. 7 raised to 2, or 7 times 7 is congruent to 49, and also congruent to 4 modulo 9 by doing some calculations. 7 raised to 3, or 7 times 7 times 7 is congruent to 343, and also congruent to 1 modulo 9. Since we already get the least residue, which is 1, it follows that order of 7 modulo 9 is equal to 3. Now that we already learned about orders of integers using modulo n, we will proceed now to the primitive roots. Primitive roots. Definition. If r and n are relatively prime integers with n is greater than 0, and if order r modulo n is equal to phi of n, then r is called a primitive root modulo n or a primitive root of n, and we say that n has a primitive root. Note on relatively prime. Two numbers are relatively prime to each other if they have no positive common factor other than 1. Take note of that. With this example 9.3, we will learn what is primitive roots. Since order 3 modulo 7 is equal to 6, this is also equals to phi of 7, because phi of 7 consists of 1, 2, 3, 4, 5, and 6. That's why order 3 modulo 7 is equal to 6, and this is also equal to phi of 7. Consequently, 3 is a primitive root modulo 7. Likewise, because order 5 modulo 7 is equal to 6, as can easily be verified, 5 is also a primitive root modulo 7. Since we already know the concept of orders of integers and primitive roots using the modulo n, we will now continue our video lesson with our part 3, which is about primality test using orders of integers and primitive roots. Primality test using orders of integers and primitive roots. Previously, we learned the concept of orders of integers and primitive roots that is necessary for this topic. In this section, we will use the concepts developed in this section to prove some converses of Fermat's little theorem, which tells us that if p is prime and a is an integer with ap, or the GCD of ap, is equal to 1, then a raised to p minus 1 is congruent to 1 modulo p. We begin with a result known as Lucas' converse of Fermat's little theorem. This result was proved by French mathematician Edouard Lucas in 1876. As we continue with our discussion, these online calculators are very useful to ease our computation. We will use these 4 online calculators in our discussion. First, I will introduce to you is the prime factor calculator. So I included the links for the 4 calculators that we will use for this discussion. For prime factor calculator, what you need to do is to input the number, the positive integer, and click calculate. Then after that, easily you will get the prime factor of that number. For large exponents calculator, this calculator is intended for those with large exponents like thousands, hundreds, and so on. Then it will easily be computed by inputting the value of x, which is the base, and the value of n, which is the exponent, and then click calculate, and it will give you the answer. For Euclid's algorithm GCF calculator, you will just input two values, the first value and the second value, to get the GCF or the greatest common factor of the two values. Then click the calculate and it will get you the answer already, easily. The power mode calculator is the useful one because it will give you already the least positive residue which is needed to compute for the power mode. You will just gonna input your base, your exponent, and your modulo. Then click compute and tada! The answer is there already. That's why you need to understand and learn how to use these 4 calculators online. But actually, we can compute it manually, but it will take time to do so. So, to ease our computation, we will just gonna use these calculators to give the best result of it. We will begin the discussion about primality test with Theorem 9.18. The Lucas converse of Fermat's little theorem, or also known as the Lucas primality test. It says that if n is a positive integer and if an integer x exists such that x raised to n minus 1 is congruent to 1 modulo n and x raised to n minus 1 divided by q is not congruent to 1 modulo n, for all prime divisors q of n minus 1, then n is prime. We will further understand the Lucas primality test with a given example. Example 9.4 for Lucas primality test. So as you can see on the upper right corner of this video, you will see the two modular equations of primality test of Lucas for us to be guided with this example. Let n is equal to 1009. Then 11 raised to 1008 because n minus 1 or 1009 minus 1 is equal to 1008 is congruent to 1 modulo 1009 by definition. The prime divisors of 1008 are 2, 3, and 7. Because from the definition, q are the prime factors or the prime divisors of n minus 1, which is 1008. And the prime divisors of 1008 are 2, 3, and 7. So how do we calculate this? A while ago, I introduced to you the online calculators for prime factor calculator. And I used that to easily get the prime factor, so you can try it later on. So we see that 11 raised to 1008 divided by 2 is equal to 11 raised to 504 because 1008 divided by 2 is 504 is congruent to negative 1 modulo 1009. So how do I get negative 1? I simply use the power mode calculator that I introduced to you with the prime factor calculator. So you can use that also. Then 11 raised to 1008 divided by 3 is equal to 11 raised to 336 because 1008 divided by 3 is equal to 336. This is congruent to 374 modulo 1009. And 11 raised to 1008 divided by 7 is equal to 11 raised to 144 congruent to 935 modulo 1009. So, we just used all the prime divisors of 1008, which is the q on the definition. So if the least or the least positive residue will not, as long as the positive least residue will not equal to 1 from the definition, hence by theorem 9.18 we know that 1009 is prime. I hope you get it, guys. We have here the corollary 9.18.1
to further support the theorem for Lucas primality test. So it states that if n is an odd positive integer and if x is a positive integer such that x raised to n minus 1 divided by q is congruent to negative 1 modulo n, and x raised to n minus 1 divided by q is not congruent to 1 modulo n for all odd prime divisors q of n minus 1, then n is prime. So here, q are all the odd prime divisors of n minus 1. So as long as our least positive residue will not equal to 1, then n is prime. Example 9.5. So this is the example for the corollary I just presented to you a while ago. So as you can see, I just I put the two equations or the modular equations on the upper right corner of this video for us to guide with this example. So let n is equal to 2003. So n minus 1 is equal to 2002. So by definition, q are all the odd prime divisors of n minus 1. So our n minus 1 is equal to 2002, and its odd prime divisors are 7, 11, and 13. So here, from the definition, we will neglect all the other prime divisors of n minus 1, and we will just get all the odd prime divisors. Here, 5 raised to 2002 divided by 2 is equal to 5 raised to 1001 is congruent to negative 1 modulo 2003. So a while ago, we said that we should neglect other prime divisors if it is not odd prime divisors. But why we put 2 here? So because it is in the definition of the corollary with the first equation above, x raised to n minus 1 divided by 2 is congruent to negative 1 modulo n. So it's still correct. So we will proceed to the next one. 5 raised to 2002 divided by 7. 7 is the odd prime divisors of 2002 is equal to 5 raised to 286 congruent to 874 modulo 2003. So how do I get 874? I just simply use the power mode calculator. So you can see that. Next, 5 raised to 2002 divided by 11 is equal to 5 raised to 183 congruent to 886 modulo 2003. And 5 raised to 2002 divided by 13 is equal to 5 raised to 154 congruent to 633 modulo 2003. So from the definition, x raised to n minus 1 divided by q is not congruent to 1 modulo n. So as long as our least positive residue will not equal to 1, if we use the second equation, the odd prime divisors of n minus 1, we see from corollary 9.18.1 that 2003 is prime.
So that's the Lucas primality test.
Another limited converse of Fermat's little theorem was established by Henry Pocklington in 1914. He showed that the primality of n can be established using a partial factorization of n minus 1. We use the usual notation n minus 1 is equal to f times r, where f represents the part of n minus 1 factored into primes and r the remaining part not factored into primes. We will further discuss that with our next primality test. This is Theorem 9.20, Pocklington's primality test. Suppose that n is a positive integer with n minus 1 is equal to fr or f times r, where f and r and their GCF is equal to 1 and f is greater than r. The integer n is prime if there exists an integer a such that a raised to n minus 1 divided by q minus 1 and n and their GCF is equal to 1 whenever q is a prime with q divides f and a n minus 1 is congruent to 1 modulo n. To further discuss this theorem or the Pocklington's primality test, I will provide you with an example. Example 9.6 for Pocklington's primality test. So remember that n minus 1 is equal to f times r, and f and r and their GCF is equal to 1, then A raised to n minus 1 divided by Q minus 1, then n, and their GCF is equal to 1. We will use Pocklington's primality test to show that 23,801 is prime. With n is equal to 23,801, we can use the partial factorization of n minus 1 equals 23,800 equals to f times r, where f is equal to 200 equal to 2 raised to 3 times 5 raised to 2, and r is equals to 119. So how do we get it? So we use the prime factors calculator and input 23,800, and the result is 2 raised to 3 times 5 raised to 2 times 7 times 17. And f from the definition are the factored prime numbers, which is 2 raised to 3 times 5 raised to 2. If you compute that, it will give us 200. And r, 119, is from 7 times 17, which are the not factored part. So that f is greater than r. To check it, 200 is greater than r? Yes, because 200 is greater than 119. Taking a equals to 3, we find that 3 raised to 23,800 congruent to 1 modulo 23,801. 3 raised to 23,800 divided by 2 is congruent to 3 raised to 11,900 congruent to negative 1 modulo 23,801. 3 raised to 23,800 divided by 5 is congruent to 3 raised to 4,760 congruent to 19,672 modulo 23,801. Again, we will use the power mode calculator to compute for the least positive residue. From this, we find using the Euclidean algorithm that 3 raised to 23,800 divided by 2 minus 1 and 23,801 is equals to negative 2. Why negative 2? Because 3 raised to 23,800 divided by 2, from the solved example above, it is equal to negative 1, and negative 1 minus 1 is equal to negative 2. And negative 2 and 23,801 and their GCF is equals to 1 using the Euclid's algorithm GCF calculator. And 3 raised to 23,800 divided by 5 minus 1 and 23,801 is equals to 19,671 and 23,801 equals to 1. This shows that n is equals to 23,801 is prime even though we did not use the complete factorization of n minus 1 equals 23,800, namely 23,800 equals to 2 raised to 3 times 5 raised to 2 times 7 times 17. We can use Pocklington's primality test to develop another test which is useful for testing the primality of numbers of special form. This test, which actually predates Pocklington's, was proved by E. Proth in 1878. Theorem 9.21, Proth's primality test. Let n be a positive integer with n equals to k times 2 raised to m plus 1, where k is an odd integer and m is an integer with k less than 2 raised to m. If there is an integer a such that a raised to n minus 1 divided by 2 congruent to negative 1 modulo n, then n is prime. Let's have an example. Example 9.7. So here, we will use Proth's primality test to show that n is equals to 13, which the value of our k times 2 and the value of our m is 8. So 2 raised to 8 plus 1 is equal to 3,329 is prime. First, note that 13 is less than 2 raised to 8, which is equals to 256. Take a equals to 3. We find that 3 raised to n minus 1 divided by 2 is equals to 3 raised to 3,328 divided by 2 equals to 3 raised to 1,664 is congruent to negative 1 modulo 3,329. That's from the definition. It follows by Proth's primality test that 3,329 is prime. The primality test of Proth has been widely used to demonstrate the primality of several large numbers of the form k times 2 raised to m plus 1.
Prott's primality test has yielded 2 of the 10 largest primes currently known, the others are Mersenne primes. For a few years, the largest known prime was one of the form k times 2 raised to m plus 1 rather than a Mersenne prime. You can run Prott's primality test and search for new primes of the form k times 2 raised to m plus 1 by yourself by downloading PC-based software from the internet. If you find one, you will achieve some fame, but not as much as if you discovered a new Mersenne prime. We are down to the conclusion of this video. What are our major takeaways from primality test using orders of integers and primitive root? There were many different ways to primality testing. Some are discussed on this study. Primality testing leads to many applications which are used up until this time. Primality testing are essential ingredients in computer security systems which includes public key cryptography and public key signatures. These schemes in particular are based on what are called RSA, revised Shamir-Adleman codes use integers of, say, 128 bits that are the product of two primes, each of about 64 bits. Elshik M. 2015 March 14. Throughout this study, we can say that testing the primality is necessary for many usage and the quest on finding the largest possible prime number is still on progress. I hope that you learned something from this video. Thank you!